looking at this huge pile of research, maybe a new paper, and you just need someone to pull out the absolute core insights for you, like right now.
Oh, absolutely. The speed things move at, especially in AI, it's easy to get buried. Trying to really grasp the key advancements, it feels like a full-time job sometimes.
Exactly. And that's what we try to do here in the deep dive. We take those complex sources, like this really interesting research paper we're looking at today, and we distill it, give you the vital stuff, maybe find a couple of those surprising insights along the way.
And today, we are definitely plunging into something pretty groundbreaking, I think, in the world of large language models.
We certainly are. We've got our hands on a paper just out, May 2025. It's called Gated Attention for Large Language Models, Non-linearity, Sparsity, and Attention Sync-Free. Whew, that's a title.
Ha, yes, it introduces this technique, gated attention, and it's already making some waves.
So our mission, our goal for you listening, is to really get under the hood here. We're not just summarizing. We want to understand the science, the principles behind gated attention, and crucially, why it's such an innovation. We'll really focus on those core scientific insights.
And then think about what it might mean for where these models are going next.
Okay, let's get into it. Gated attention. Now, the paper mentions gating mechanisms aren't totally new in neural networks. What's the basic idea? When I hear gate, I think, opening and closing, letting things through or stopping them.
That's actually a perfect way to think about it. A gating mechanism, fundamentally, it's like a smart valve or filter for information in the network. It learns to control the flow.
Okay.
So based on the situation, the input, it can selectively let certain signals pass, maybe amplify them or restrict others. You saw early versions of this idea in things like LSTMs, remember those, and highway networks.
Right, yeah, LSTMs used gates to manage memory, didn't they? And highway nets for deeper training.
Exactly. They were crucial for handling sequences or enabling those really deep networks back then. So the concept has history.
Okay, so how does that idea, controlling information flow, plug into the attention mechanism that's so central to modern transformers? The standard attention, softmax attention, right?
Right. So standard attention lets the model weigh how important different input parts are when it's processing something. Gated attention adds another layer on top of that. It lets the model actively modulate or fine-tune that standard attention output, like adding that dynamic valve you mentioned to the attention pipeline.
A dynamic valve, I like that. So it's not just passively calculating weights, it's actively controlling what gets through based on those weights. How did that work, like technically? The paper gives this formula, y prime equals y circle dot sigma of xw theta. Can you unpack that a bit?
Sure. So y is basically the normal output of the attention mechanism. The formula says we take that output y and we multiply it, that's the circle dot element-wise multiplication, by a gating signal.
Okay.
And that gating signal is calculated from some input x using learned parameters w theta and then squashed through an activation function sigma, usually a sigmoid, which puts the values between 0 and 1.
Ah, so the gate calculates a score between 0 and 1 for each part of the attention output based on some other input and uses that score to scale the attention. 0 means block it, 1 means let it through fully.
Precisely. It's a learned input-dependent filter. It decides contextually which parts of the attended information to emphasize or de-emphasize.
Okay, that makes sense. Now, the researchers didn't just try one way of doing this. They explored, 5 key aspects? What were the dimensions they were playing with here?
Yeah, they were really systematic. They looked at 5 main things. First, the position, where exactly in the attention block do you put this gate? They labeled these G1 through G5 in their diagrams.
Right.
Second, granularity, do you apply the gate to the whole attention head output at once or element by element? Third, head specificity, does each tension head get its own independent gate or do they share parameters?
Okay, specific versus shared gates.
Fourth, multiplicative or additive gating, are you scaling the output, like in the formula we discussed, or adding something? And fifth, the activation function for the gate itself, sigmoid, or maybe something else like Zeyu.
Lots of variables to test. And through all that testing, they found something really stood out, didn't they? This G1 position gating after the main attention calculation.
Yes, that was the clear breakthrough finding. Applying a head-specific sigmoid gate right after the scaled dot product attention, that's the SDPA part, the core attention calculation, this G1 position consistently gave the best results.
And not just slightly better.
No, significantly better. They saw perplexity reductions, which means the model got better at predicting text of up to 0.2 ppl and, maybe more strikingly, up to a 2-point jump on the MNLU benchmark.
Wow, 2 points on MMLU is definitely not trivial. That tests some pretty complex understanding.
Exactly, and this was on their bigger 15 billion parameter mixture of experts models. But importantly, they saw similar positive trends on smaller 1.7 billion parameter dense models too.
So it seems robust across different model sizes and types. That's a good sign. Did it offer any other advantages besides just better scores?
It did, and these are quite important from a practical training perspective. They observed much better training stability, fewer of those big sudden jumps in the loss value that can really mess up training large models.
Ah, the dreaded loss spikes. Yeah, taming those is huge.
Absolutely. And because it was more stable, they found they could use larger learning rates effectively, which, can speed up training and potentially lead to better final models. It also suggests better scaling properties overall.
Okay, so better accuracy, more stable, potentially faster training. That G1 gating seems like a real win. Now, let's get into the why. The paper really digs into the scientific reasons, focusing on nonlinearity and sparsity. Let's unpack the nonlinearity part first.
Right. This is where we get into the core scientific contribution, I think. The researchers argue that the standard attention mechanism, specifically the value projection, WV, and the output projection, WO, can essentially be viewed together as one combined low-rank linear transformation.
Low rank, meaning it's mathematically limited in the complexity it can represent, like a bottleneck.
That's a good way to put it. It inherently limits the richness of the transformations the attention layer can perform. Now, here's the key insight. By inserting the gate with its nonlinear activation function, like the sigmoid at the G1 position, or G2, which is similar, you break that linearity.
You're injecting nonlinearity right into that transformation path.
Exactly. You're increasing the mathematical expressiveness of that step. The model can now learn much more complex nonlinear relationships between the attended information and the final output of the attention layer. It just gives the model more power, mathematically speaking.
That makes intuitive sense. More complex tools for a complex job. And didn't they find some supporting evidence for this idea using RMS norm?
Yes, that's right. They tried adding RMS norm, which is another way to introduce a form of nonlinearity at that same point, and it also reduced perplexity. It wasn't as effective as the gating, but it supported the general hypothesis that adding nonlinearity there is beneficial.
Okay, so nonlinearity boosts the expressive power. What about the second factor, sparsity? How does the gate make things sparse, and why is that a good thing scientifically?
So the sigmoid gate outputs values between 0 and 1. When you multiply the attention output by these values, anything multiplied by a score close to 0 gets effectively suppressed or pruned away dynamically.
So it's like the gate learns to ignore certain parts of the attention output that aren't relevant for the current context. It's not random pruning, it's learned input-dependent filtering.
Precisely. It induces input-dependent sparsity. And what the researchers found, which is really interesting, is that the configurations that worked best, the G1, element-wise, and headwise gating, actually had the lowest average gating scores.
Wait, lower scores were better, meaning they were more sparse.
Exactly. It suggests the model benefits significantly from actively filtering out or zeroing out a good portion of the calculated attention output. It forces the model to focus on the most salient signals, making it potentially more robust to noise or distraction in the input.
That's counterintuitive, but powerful. Ignoring things helps you focus. And the paper stressed that this sparsity needed to be head-specific. Why was sharing the gate bad?
Well, different attention heads in a transformer tend to learn different things, right? They specialize in capturing different kinds of patterns or relationships. Maybe some focus on syntax, others on semantics, short-range dependencies, long-range ones.
Right, they're like little specialists.
Exactly. So if you force them all to use the same filter, the same gate, you're hampering their ability to do their specialized job effectively. Allowing each head its own gate lets each specialist fine-tune its own output optimally. Their experiments clearly showed performance dropped when gates were shared.
Okay, so head-specific gates let the specialists work best. And one more nuance here, query dependency. Why did that matter for the sparsity?
This relates to what information the gate uses to decide what to filter. For the best performing G1 gate, the gating score depends on the query basically, the representation of the token the model is currently focused on processing.
So the filtering decision is directly related to what the model is trying to figure out right now.
Yes. Contrast that with, say, G2 gating, which depends more on the keys and values, past information, or input-independent gating, which, unsurprisingly, performed much worse. Query-dependent gating means the sparsity is highly contextual and tailored to the immediate task, which seems to be the most effective way to filter irrelevant information.
Okay, so we've got nonlinearity for expressiveness and this targeted, query-dependent, head-specific sparsity for focus. Now, that paper title also had attention sink free in it. That sounds important. What exactly is an attention sink?
Yeah, this is another really significant innovation highlighted in the paper. The attention sink is this phenomenon researchers observed where in standard transformers, the very first few tokens in the input sequence Often just the absolute first token, like a start a sequence token, tend to grab a huge amount of attention from all the subsequent tokens, layer after layer.
Like they just suck up all the attention, a bottleneck.
Pretty much. They become these sinks where attention disproportionately accumulates. Scientifically, the concern is that this might prevent the model from paying enough attention to potentially more relevant information that appears later in a long sequence. It's an inefficiency baked into the standard architecture.
Okay, that definitely sounds like a problem, especially if you're dealing with long documents or conversations. How does this G1 gating fix that?
This is one of the most striking results they present. Their analysis, using visualizations and quantitative metrics, shows that the SDPA output gating the G1 configuration practically eliminates the attention sink.
Eliminates it completely.
Almost entirely. They show the attention paid to the first token drops dramatically. I think the number was from something like 46 or 47% in the baseline down to under 5% in the gated model.
Wow, that's a massive shift in the attention patterns. How does the gating achieve that scientifically?
The hypothesis is that the sparse query-dependent filtering is key. By dynamically pruning away less relevant connections based on the current query, it prevents those initial tokens from just passively accumulating attention by default. It forces a more deliberate and distributed allocation of attention across the sequence.
So it stops that initial pileup.
Right, and importantly, they compared this to value gating G2. While G2 did reduce some large activation values, it didn't fix the attention sink problem nearly as effectively. This really highlights that gating the SDPA output G1 in that query-dependent way is scientifically distinct and uniquely beneficial for this issue.
So getting rid of this attention sink, that must have downstream benefits, right? The paper connects this to handling longer contexts, which is another major challenge for LLMs.
Precisely. This is presented as another key innovation stemming from the attention sink-free property. They tested the models on much longer sequences, pushing the context out to 64,000, even 128,000 tokens, using techniques like rope scaling and yarn.
Okay, really long sequences. What happened?
Well, as you'd expect, performance does degrade for both the baseline and the gated models when you stretch the context that far. Still a hard problem. But the crucial finding was that the gated models significantly outperformed the baseline models at these extended lengths. Their performance drop was less severe.
So they were more robust to the context getting really long.
Exactly. They seemed better able to actually use information from way back in that massive context.
And the scientific thinking is that the baseline model's reliance on the attention sink somehow hurts it when the context gets super long, whereas the gated model, being sync-free, adapts better.
That's the theory they propose. The baseline might be using the sync as a sort of crutch that fails at extreme lengths, while the gated model's more flexible, input-dependent attention distribution makes it inherently better suited for long-range information processing.
This is fascinating. It feels like this SDPA output gating is a really elegant and powerful tweak. So summing up the broader implications here, what are the key scientific takeaways?
I think the main takeaway is that this relatively simple modification, adding a specific type of gate, head-specific sigmoid, right after the SDPA calculation G1, delivers a cascade of benefits. You get increased non-linearity and expressiveness, useful input-dependent sparsity, you fix the attention sink problem, and as a result, you significantly improve long context performance. It addresses multiple known issues with one mechanism.
And they're planning to release these models?
Yes, they mentioned planning to release their attention sink-free models, which is great for the community. It allows others to verify, build on, and really explore these findings further. Open science in action.
Fantastic. Now, like any good research, they probably acknowledge limitations or open questions, right? What's still needed from a scientific standpoint?
Definitely. They point out that while the empirical results are strong, a deeper theoretical understanding is still missing. Like, precisely how does the introduced non-linearity interact with the attention dynamics? And what's the exact theoretical reason why eliminating the attention sink leads to better long context generalization? There's a clear correlation, but the formal link needs more work.
So the what is clear, but the deep why still has some gaps. What kind of future research does this open up, do you think?
Oh, several exciting directions. People will likely explore different activation functions for the gate, maybe different gating structures entirely, optimized for specific tasks. More theoretical work is definitely needed on sparsity and its role, and of course applying this to even larger models, different modalities. Seeing how well these benefits scale and generalize is crucial.
It really feels like a significant step forward. This has been a fantastic deep dive, really getting into the scientific meat of gated attention. For you listening, we really hope this gives you that solid, thorough understanding of what makes this technique innovative and why it matters for the future of LLMs.
Absolutely. And it does leave you with a kind of provocative thought, doesn't it? This idea of an attention sink in AI. Makes you wonder if there are analogous processes in, say, human cognition, ways our own attention might get stuck on initial information, perhaps hindering broader understanding. It's an interesting parallel to consider from a scientific perspective.
That is a fascinating thought, how we filter and focus. Definitely food for thought. Thanks so much for walking us through this research today.
My pleasure. It was great digging into the science behind it.